Okay, so our first example, and like I said, I'm just going to give you this example. We'll walk through the steps of exactly what I want you to do, and then you guys are just going to know it, okay? So, data provides phosgene gas. It's a special World War I gas that they used to poison troops back in the day, okay? Is composed of 12.1% carbon, 16.2% oxygen, and 71.7% chlorine, and has a molar mass of 98.8 grams per mole.
Leave him out.
That's percentage, right? Or that percentage or slash? Make that up.
What? That's just in my example here that I always use.
Okay, so it's 6. What?
Sometimes I don't use notes, I guess, but okay.
Just so I can.
So the first thing that you're going to do, okay, what this is telling us is that we've got this unknown substance that has carbon, oxygen, and chlorine, okay? Now, based on this, running this through on a combustion analysis, this is like the numbers that it kind of like spits out at us to let us know that the total molar mass of however these carbon, oxygen, and chlorines are combined is giving us a molar mass of 98.8 grams per mole, okay? Then that's also telling us that about 12.1% of that particular substance is made up of carbon. Oxygen is 16.2% of that 98.8%, or grams per mole, sorry. And then 71.7 is chlorine composition, okay? So where this is going to help us is that we're actually going to figure out what the chemical formula for this is, and then because you guys have been working on molecular structural diagrams, you guys are actually going to be able to predict what the structure should look like, okay? Unless I otherwise specify. So, this is how you do this. So you start off with your carbon, your oxygen, N, okay? N stands for how many moles of that substance you'll actually have, okay? All right. So that's your first step, is that you're going to like kind of split those up into the 3 categories, or 4, or however many kind of atoms are participating in there, okay? So the first thing that you're going to do is you're going to take your carbon. We'll only look at that one first. So carbon is 12.1%. So instead of actually leaving it as a percentage, I have to put it in as a proportion, so a decimal place of that percentage. Number one error that people will make is they forget to convert that percentage. Otherwise, they do everything right. That's like the number one error that people will make, okay? So if it's not the same thing, okay? So 12.1% of that molecule of 98.8 grams per mole molar mass of that substance is going to be made up of carbon. So we're going to actually multiply this out by the total molar mass of the substance, because that tells us how much proportion of that molar mass should be dedicated to just carbon. And then what we're going to do is we're actually going to divide it by the molar mass of a single atom of carbon, okay? Here's the other thing. You don't want to just say that it's like oxygen, because oxygen is actually O2. You're only worried about the actual number that you pulled directly out of your data booklet. So for carbon, it's 12.01 grams per mole. And that'll tell you how many moles of carbon are actually in the formula. So when we calculate this out in our calculator, okay, so 0.121 times 98.8 divided by 12.01, we're going to get, sorry. All right, so This is approximately 0.995, blah, blah, blah. Don't worry about significant digits here because we're talking about moles in the actual chemical formula. Okay, so for this one right here, it's safe for us to assume, and we round this in a logical way, that we can say that there's at least one carbon molecule in here. Okay, so we'll say that there's one carbon in the chemical formula. Okay, then we do the exact same thing to the oxygen. So oxygen is 16.2%. So we're actually going to convert this into the decimal form. We're going to figure out how much this is proportionate to, it's in the question right here.
Where'd you get 12.0?
That's from your data booklet. The molar mass of the carbon atom. Okay? All right. So, then you divide it by the atomic molar mass of just one oxygen, okay? I know that the molar mass for oxygen as an O2 molecule will be 32 grams per mole, but in this case here we're only interested in the number of atoms on their own, okay? So this is going to be divided by 16 grams per mole, okay? So oxygen, once we calculate this out, okay, we get 1.000 blah blah blah. So it's pretty safe to assume how many oxygen atoms are we going to have in this chemical formula? 1. Okay, so far our chemical formula is telling us 1 carbon, 1 oxygen. That's it. Okay, now chlorine, we do the exact same thing. Okay, so we have to first convert that percentage into a decimal, so 0.717 times 98.8 grams per mole, that's the total molar mass, and then we divide it by what value? 35.45 based on one atom only, okay? I know it's that chlorine as a Cl2 molecule has a different molar mass, but this is only per atom. Okay, so 35.45 grams per mole. So this will be 1.981574048. Okay, so 1.998 blah blah blah. Okay? So, if we were to round this, it's safe to assume how many chlorines will we have in this chemical formula? 2. Okay? So, at the end of this, this is what we have found. This is the chemical formula for our molecule that we've just put through this like little special machine that did a combustion analysis. They basically burn it, the percentages come out, there's a total molar mass, and then you can kind of figure out what the composition of that substance is.